Okay, welcome back everybody. So this is the 12th video of the series. However, the topic is called partial fractions, but I'm breaking this up into two parts or two videos because this is a fairly long topic to explain, and I wanted to make the videos a little bit shorter. So in this video we'll be discussing the four cases of partial fractions with, of course, what I like to call the special case, and how we incorporate or how we connect this to integration. So this is the first part of the video, and I will be posting also the second part very soon. So what is the idea of partial fractions? Well, going back to what we did in secondary 4, we had these two rational expressions and we were asked to add them. So what we needed to do was find a common denominator. In this particular case, the common denominator was x minus 1 times x plus 2. So I found the common denominator. There we go. We simplified. We combined similar terms and we end up with an answer of 5x plus 1 over x minus 1 times x plus 2. Okay. However, now in Cal 2, what we're doing is we're going to work backwards. In other words, we're going to decompose this. So we're going to be given this particular question, and we're going to have to somehow decompose it or break it down into two parts in this particular case. So in other words, what we've done in the past is combine the two fractions together or the two rational expressions together. Here we're given one rational expression and we're going to have to break it up into as many parts as possible, hence partial fractions. So let's get started with the first case. So the first case says this: the denominator has distinct linear factors. Now the word distinct means they're different. So it looks something like this. We have a polynomial in my numerator, and we have these distinct linear factors in my denominator. So for example, 2x plus 1, or x minus 3, or 2x minus 7, whatever the case may be. So as long as we have distinct linear factors in my denominator, we fall under case 1. So the next thing we need to look at is to make sure that the degree of the numerator is less than the degree of the denominator. And when it is not, well, I'll show you later on in the second video what we do in this particular case. However, as long as the degree is less than the degree of the denominator, then we are okay. We have the distinct linear factors. We fall under case 1, and I'm going to show you now the process for case 1. So this is the process. We start off with this rational expression that has distinct linear factors in the denominator, and we're going to break them up into each part. So in other words, each distinct linear factor will have a numerator, which we will call a1, a2, a3, all the way up to a sub n, depending on the number of linear factors we have. So although this might look a little bit confusing, this is really what it comes down to. So taking a look at the previous example, we have 5x plus 1 over x minus 1 times x plus 2. How would I break this up? Well, I have two distinct linear factors in my denominator. So technically the first one would be a1 over x minus 1, plus the second one would be a2 over x plus 2. Next example has three distinct linear factors. So I would put a1 plus a2 plus a3. So this is the process for trying to break it up into partial fractions. Okay, so let's take a look at an example. We have 5x plus 1 over x squared plus x minus 2. We have a trinomial in my denominator. Let's see if it's factorable, and it is. We have x minus 1 times x plus 2. Fantastic. Since we have two distinct linear factors, what I'm going to do is I'm going to break it up into two parts. However, instead of using a sub 1 and a sub 2, what I like to use is the letters of the alphabet. So a plus b plus c, and so on, depending on the number of distinct linear factors. It's a lot easier to work with A's and B's and C's than it is to work with a sub 1, a sub 2, and so on and so on. However, that's my opinion. If you prefer using the a sub 1 and a sub 2, you're more than welcome to. Alright, so what's the process exactly? Well, what we're going to do is this. We know that this particular rational expression is broken up into two parts because there are two distinct linear factors. And now what I'm going to do is I'm going to multiply by the LCD. Now, how do I figure out what the LCD is? Well, I look what's under the original expression that's given to me. So x minus 1 times x plus 2. Because what my goal is to get rid of my denominators and end up with a linear expression or a linear equation. So I'm going to multiply the left side by x minus 1 times x plus 2. I'm going to multiply the right side by x minus 1 times x plus 2 and x minus 1 times x plus 2, cancel out the common factors, and I end up with a linear equation. That is my goal for now. So that's the first step. The first step is in trying to create a linear equation. So, create a linear equation is my first goal. My second goal will be to choose a particular x value that will eliminate one of the variables so that I can solve for one and eliminate the other. Because right now, as it stands, I have two unknowns. I have a, which I don't know, and b, which I don't know. So by choosing a particular value for x, I can eliminate one of those variables and solve for the one that I'm looking for. So let's continue on the next slide. We have our linear expression or linear equation. And what I decide to do is I decide to let x equal to 1. Why do I do this? Because I want to eliminate one of the variables, and by choosing x to be 1, I end up eliminating b. So what I do here at this time is I simply replace all the x's with 1. So I get 5 times 1 plus 1 is equal to a times 1 plus 2 plus b times 1 minus 1. And as you can see, 1 minus 1 is 0. 0 times b is simply 0. I eliminate b. And what this allows me to do, it allows me to solve for a. Great. I already found one value. Now I'm going to do this again. So replace a with 2. And now once again, choose a value of x that will allow me to solve for b. In this particular case, I can choose x to be anything but 1, because if I chose 1 again, it would definitely cancel out the b, and that's what I don't want. So what I decide to do is choose x to be negative 2. I decide to eliminate the first part. I could have chosen x to be 0 if I wanted to. Okay, so as long as I don't choose b to be or x to be 1 in the second case, all is good. So replace x with negative 2. We get 5 times negative 2 plus 1. Negative 2 plus 2 is 0. That cancels out. And then, of course, negative 2 minus 1. When I solve for b, I get b to be 3. Well, there we go. We just broke it down into partial fractions. 5x plus 1 over x minus 1 times x plus 2 is equal to 2 over x minus 1 plus 3 over x plus 2. And there you go. Okay, so how do we connect this to the integration or finding the antiderivative? Well, this is the question you would be receiving. This is the question they're giving you. Find the antiderivative of 5x plus 1 over x minus 1 times x plus 2. Now, since it doesn't fit any of the previous patterns that we've seen, we're going to try this new thing, which is partial fractions. Now, we've already worked on partial fractions. We used the same example we did in the previous slide, and we ended up with this. So this is the way I would break it up into partial fractions, into parts. And in this particular example, I have two parts. So finally, all I need to do is find the integral of the first one plus the integral of the second one. And we factor out the 2 and 3 because they're constants. Now it starts to resemble the logarithmic integration, which is u prime over u. And therefore, my final answer is simply 2 times the ln of the absolute value of x minus 1 plus 3 times the ln of the absolute value of x plus 2. And don't forget to add my c as my constant. Now remember that this also works for definite integrals. Remember that definite integrals and integration, or finding the antiderivative, are very, very similar. One allows me to find the function, the other one allows me to evaluate it. Okay? But the process for partial fractions is identical. It is the same. Okay, so for this particular example, I would like you to try it out. So pause the video and try to, first thing, break it up into your distinct linear factors. So this is what you should have obtained. And then, of course, you're going to turn this into a linear equation, which means multiplying through by the LCD. You're going to solve for A, you're going to solve for B, and you'll solve for C. So once again, do that on your own. Pause the video. And this is what you should have obtained. 2 over x minus 3 minus 1 over x plus 2 plus 5 over x minus 1. Now, if you didn't get these, chances are you just made some kind of algebraic mistake. So usually most students, they make a, quote unquote dumb mistake, and that's why they're unable to find these. But normally, it's really, really smooth. And this is what you should have obtained as your values of A, B, and C, or once again, A sub 1, A sub 2, or A sub 3. So the question you would get would be something like this. Find the integral of this particular function. Now, you would, of course, find the partial fractions and then simply integrate each of those parts. Okay, so this is the second case, and in this particular case, what you'll notice that the denominator has repeated linear factors. So in other words, it's one linear factor that has a power to it. So once again, extremely important that the degree of the numerator has to be less than the degree of the denominator for this particular case to work. Now we'll see later on in the video, in the second part, what happens when the degree of the numerator is greater than that of the denominator. But for now, this is case number 2, where the degree of the numerator is less than the degree of the denominator, and of course the denominator has repeated linear factors. So let's take a look at the process. So here's the process for the repeated distinct linear factors. So we have to the power of n. So what we're going to do is we're going to increase until we get to the power of n that they give us. So for example, the first one would be a sub 1 over ax plus b to the power of 1. The next one, a sub 2, ax plus b to the power of 2, to the power of 3, to the power of 4, so on and so on, until we get to the number of powers that they tell us. So it's always put in increasing order. So if, for example, it was ax plus b to the power of 5, then the first one would be to the power of 1, to the power of 2, to the power of 3, to the power of 4, and finally to the power of 5. And I'll give you a couple of examples later on to show you exactly what I'm trying to explain. But this is simply the process for case number 2. So this is what I'm trying to explain. Here we go, we have this function x minus 3 over x minus 2 all squared. We have a distinct linear factor in the denominator. It has a power of 2, so we're simply going to break this up into 2 parts, whereby the first one is to the power of 1 and the second one to the power of 2. For the second example, this one's a little bit different because it's a combination of 2 cases. The first part, x, which is the first case, and the x minus 3 cubed, which is the second case. So it's also possible to combine cases together. So what we end up with is this, a over x, because it's a distinct linear factor, and then of course to the power of 1, b, to the power of 2, c, and finally to the power of 3, d. And once again, the process would be the same. Multiply everything through by the LCD, make a linear equation, and solve. So let's take a look at an example. We're given this particular rational expression. We have a denominator, which is x plus 3 to the power of 2. So we're going to break it up into 2 parts, because the first one will have a power of 1 and the second one will have a power of 2. And once again, like I said earlier, instead of using a sub 1 and a sub 2, I decided to use a and b. So what we're going to do now is simply multiply through by the LCD and of course get it into a linear equation. This one is a lot easier because all I'm going to do is simply get rid of the a. And I'm going to do this by letting x equal to negative 3. Replace x with negative 3, solve for b, and b is equal to negative 4. Fantastic. Now, once again, the equation has to be redone or rewritten with b being negative 4, and I will choose x to be 0. In doing so, I can now solve for a. Solve for a, and I get a to be 7. So, my partial fractions, 7x plus 17 over x plus 3 all squared is equal to 7 over x plus 3 minus 4 over x plus 3 all squared. Okay, so you should try this example. Put the video on pause, see if you can break it up and eventually find the values. So here we go. This is what you should have gotten. Breaking it up, a over 2x plus 1 plus b over x minus 1 plus c over x minus 1 all squared. And once again, if you want, pause the video again, work it out, multiply everything through by the LCD, and the answers you should have obtained were this. So a should have been 11 thirds, b should have been negative 7 thirds, and finally c should have been negative 4. Now remember, you cannot write 11 thirds over 2x plus 1, so it becomes 11 over 3 times 2x plus 1, minus 7 over 3 times x minus 1, and finally minus 4 over x minus 1 all squared. Now once again, this is not integration, this is simply breaking it up into partial fractions. Okay, so making the connection to integration, this would be the particular question you got. Find the integral of this rational function, and therefore you would realize that you'd have to break this up into partial fractions, and we just did this previously. Remember that 11 thirds is a constant, okay, so it can be factored out. Negative 7 thirds or 7 thirds is also a constant which can be factored out, and finally negative 4 is also another constant that can be factored out. Now that we broke it up this way, we simply integrate each part, and we end up with this particular answer, which is simply 11 over 6 times the ln of the absolute value of 2x plus 1, minus 7 over 3 times the ln of the absolute value of x minus 1, and then finally 4 over x minus 1, and don't forget to add my constant plus c. So here's the connection between partial fractions and integration. Since I decided to make these videos a little bit shorter, I strongly suggest that you watch the second part of video 12, which will actually involve working out cases 3 and 4, and of course that special case that I mentioned earlier.